Right, okay, we've got a video here. It's a couple of worked examples for integration by substitution, but not the reverse chain rule in this case. What we're actually doing is we're using substitution really to sort of simplify the expression that that we're integrating. So if we've got something like this here, this is a composite function times the product with another function here, dx, then if we do the substitution u equals f of x, then what we're going to get is this here, which will help us, because if this composite function here usually kind of gets in the way, and we're going to end up also with well, the h of x stays, and then our dx becomes this expression here, du over the derivative of f with respect to x. Now this thing here potentially got a cancellation, and we're going to form a new function here in x, which we can then translate into u. So we're going to end up with something like this, which with any luck should be a bit simpler. So this particular example, we got the integral between 0 and 3 of x to the power of 5 square root of 1 plus x cubed dx. Now this is our composite function here. The g is the square rooting, and the f is the 1 plus x cubed. So so basically that's what we're doing. Now you don't need to remember all this h's and f's and h's. I think really it's just to give you a little bit of idea of what we're doing. Usually these things are it's fairly obvious what the substitution is going to be, and in some cases it will even be told, you know, the question, particularly at A level, will be, you know, let u equals something or other. Okay, so let's forget all about the h's and f's and so on for the moment, and let's just bang on with this. Where, well, what we're going to do here, see, this is our f here. So this is the substitution we're going to do. U equals 1 plus x cubed gives us du equals 3x squared dx. And just turn this around, we've got x cubed equals u minus 1. Okay, so the integral becomes this thing. Now, I've still got my x limits here, so I've actually made this sort of explicit that it's an x, they're x limits by writing it like this. It helps me to remember, you know, not to use them as u limits. And then we've got our x to the power of 5. Our square root of u, and then our dx comes in here. Now you can see we've got some cancellation going on. We take this third out, and then we cancel the x to the power of 5 and x squared, giving us this x cubed with our square root of u du. Okay, now our x cubed actually then is quite nice, because that is u minus 1. You can see from here. So we got u minus 1 into the square root of u du, with the third outside. So we can just multiply that out, and here we go. So we, you know, had a stroke of luck here, haven't we? U to the power of 3 over 2 minus u to the power of half du, and we integrate that, and we get this expression. So this is just the power rule that we're using here. And okay, and so that is the result. We've still got to evaluate between x equals 0 and 3. Now at this point we could actually swap our limits. If we you know, we can calculate our u limits just by playing this little formula here. So x, when x equals 0, u equals 1, x equals 3, u equals 28. So that will be one way of doing it. We could just calculate it like that. I kind of quite like to convert it back. Don't know, just personal preference, I think. And so what I've got here, I mean, I've not typed it out. What I've actually used is to check my result, as I use this resource here, integral-calculator.com. So if you're not aware of that, I suggest you have a look. It is a brilliant piece of work. and will do your integrals for you. Now, I'm not suggesting that you use it to do exercises that you've been set, you know, in your class. But if you want to check your results, then it's really, really, really useful. There's also a nice piece of text on there as to how it works, which is actually quite interesting. So that gives us this this particular expression here when we substitute back in our x's for the u's, so that you can see that this is kind of directly from that, and then when we evaluate it between our x limits, we're going to get this this thing. I'm not trying truncating it or rounding it, so that is the result of all that. So that is it, and yeah, so it's kind of, you're moving complexity, really. That's the way I like to think of it, is you know, we've got two lots of complexity all in one here. Let's just let's simplify it. So so that's one example. Now let's have a look at this example, because this is very much in the same vein. And now here we've got, now this is got a square root on the denominator. I mean, when we think about it in terms of the powers of x, we've got x to the power of 1 on the top, and we've got x to the power of a half on the bottom. So this whole thing should be sort of the order of x to the power of a half, really, shouldn't it? All right, but unfortunately, because this 2 and this -1, they kind of get in the way of all that. So well, here we go. It gives us a substitution here. U squared equals 2x minus 1. I'll come back to this statement here. So here we got that. So then if we differentiate, we get 2u du equals 2 dx, and therefore dx equals u du. If we turn this one round, we've got this expression for x. And on this situation, I have actually calculated the u limits. Right. So now our integral becomes 3x, that's the numerator there. We've got u on the bottom. We substitute u squared equals 2x minus 1. So this is just u on the denominator. And then our dx becomes u du. Okay, and this expression therefore is going to be and these I've actually switched my limits here, because I've got a du operator here, so I've got the limits of 1 and 3. So this is the expression that we are integrating. Now this is obviously pretty straightforward. It's just the power rule. So yeah, what have we done? We've kind of moved our we've basically moved our complexity, and we were sort of taking the complexity out of this. I mean, it's not only a square root, but it's also a negative as well. So it's so we've got something nice and simple here. Then it's kind of moved the complexity into the numerator, isn't it? But we can cope with it in the numerator somewhat better. So that's what we've got. Integrates to that. We apply our limits between 1 and 3, and basically that evaluates to this. You can pause the video and just check that through for yourself if you like. Which work that through, and that's going to be equal 16. So that is the result of this. And as I say, in this case, we've actually done it not by switching the expression back to in terms of x, but left it in u, but changed the limits. So I think there's the potential thing when you do change the limits as to whether or not you've actually, you know, if you have square roots involved, whether it's actually a negative or a positive square root. But in this case, the implication of this, and we're actually using u squared equals 2x minus 1. So if x is equal to 1, then u squared equals 1. Question would be, does that mean that u is minus 1 or plus 1? But essentially, but really, this is what we're doing here, is we're actually using the square root. So without kind of going into massive detail on that. It's basically, that's why we take the positive square root of our when we're taking our u-limits. Right, okay, so that is integration by substitution, where we're basically just trying to simplify things. Very often you'll see sort of nasty looking things on the denominator, and if we can actually, which of course is actually, if it's on the denominator, we can think of it as being a composite function, because it's whatever that expression is to the power of -1. So your G is the power of -1, and your F is whatever expression we've got here. So, that's the kind of thinking. So I hope that's been helpful. And okay, thanks for listening.